Surprise is these primers are made out of RNA. So the first thing that is synthesized during DNA replication is RNA. It's a short 30 bases or so of RNA chain synthesized by the primase enzyme so that complementary and anti-parallel RNA monomers are strung together. 20 or 30 of them, not very many at all. So I am carefully and deliberately indicating my 3' ends with these arrowheads, which is everybody's convention, I think, worldwide. What that primer is providing for us is a 3' hydroxyl. So at the arrowhead, we always can picture a 3' hydroxyl. And we saw already how that hydroxyl is an important component to allow a condensation reaction to take place. That 3' hydroxyl is the substrate for the next enzyme, which we will call the DNA polymerase for extension. So the DNA polymerase for extension will polymerize DNA monomers because it sees that paired hydroxyl sitting across from a template strand as its substrate. It will grab that 3' hydroxyl and it will extend, following the instructions in the single-stranded template. And of course, this bubble is going to keep opening up, and more DNA will be copied that way. Up here, the same thing is happening. The DNA polymerase for extension finds that 3' hydroxyl and will extend. Once it starts, it just keeps going until it falls off the end of the chromosome. That is said to be continuous. Up here as well, continuous. But meanwhile, as this bubble is opening to allow continuous replication, it's exposing some single-stranded DNA over here. That single-stranded DNA is the substrate for primase. Primase will come in and lay down a short primer here, here. As soon as that 3' hydroxyl is recognized by the DNA polymerase for extension, that gets extended until there's no more available template. Meanwhile, the bubble's gotten bigger. Primase lays down more primer. As soon as that 3' hydroxyl is recognized, it is extended until we run out of template. Meanwhile, more single-stranded DNA template allows primase to build a primer, and that gets extended by the DNA polymerase for extension. So what we've described here and here is discontinuous. And so DNA replication is both continuous over here and discontinuous over there, and so we use the word semi-discontinuous. Now, diagramming this, it seems like the continuous synthesis ought to be quite easy. You start and you just go. And it took on the name leading strand. On the leading strand, or leading strand synthesis, is said to be continuous. Compared to, they assume on the other strand, the lagging strand, discontinuous synthesis seems so much harder. You have to start and stop and start and stop and start and stop. It must be slower. That turns out to be completely wrong. We'll see a diagram in a minute, an animated diagram that shows synthesis on the leading and the lagging strands are exactly simultaneous. So those names seem to have stuck, but they can be misleading. Now, what we can see here is this is not what we wanted. We've got bits of RNA and DNA. We've got these little segments here that are not covalently bonded yet. Remember, the beginning of my arrow is a 5' end with phosphates out there. The arrowhead is a 3' hydroxyl. These pieces are said to be fragments. These fragments are named Okazaki. And at this point, they are indeed composed of both RNA and DNA. And so what happens next, because clearly we have to get closer to what we're looking for, we have contributions by another enzyme, the DNA polymerase 4 repair. The DNA polymerase 4 repair will see this little section of RNA across from DNA. That so-called duplex, an RNA-DNA duplex, that looks like DNA damage to the DNA polymerase 4 repair. And its job is to get rid of the damage and at the same time extend that 3' hydroxyl to fill in the gap. So the DNA polymerase 4 repair is cutting out the RNA and extending the previous 3' hydroxyl to fill in the gap. And so it takes another enzyme to clear up this problem, the problem of the RNA-DNA duplex. Now, before we go any further, we have to stop and give some details. We have to compare prokaryotes versus eukaryotes. Now, in prokaryotes, students are expected to know by name the DNA polymerase 4 extension is DNA Pol 3, Roman numeral 3. And we're going to see there's a nasty reason why they want you to know that, but that's an absolute testable, trivial fact for undergraduates of molecular biology. The DNA polymerase 4 repair in a prokaryote is called DNA Pol 1. I've never heard anybody tell me what DNA polymerase 2 does. I think it can be deleted from the cell and the cell doesn't even miss it. So they've broken this down to the polymerase for extension is Pol 3, the polymerase for repair is Pol 1 in prokaryotes. Now, when we shift over to think about eukaryotes, the general theme is eukaryotes have more specialists. There are 20 different DNA polymerases in eukaryotic systems, 20. They don't go by Roman numerals at all, they go by Greek letters of the alphabet. I've never, if you go to Wiki, you can read about alpha, beta, you can read about the whole list. There's a lot of confusion about exactly what's going on. So what I find is that undergraduates are thinking about eukaryotes will imagine that somebody is the DNA polymerase 4 extension and we don't worry about naming names. But DNA Pol 3, you're talking prokaryote. Now, when it comes to eukaryotes, the DNA polymerase 4 repair, again, we will just call it the DNA polymerase 4 repair. We don't know which. It's probably several of the DNA polymerases specialize in repair. But the important thing that they want students to know is in eukaryotes, these DNA polymerases for repair only fill in the gap. The gap gets made by another enzyme that is strictly eukaryotic called RNase H. And that seems like a trivial detail, but we're going to see RNase H again in the course several times. This is where it comes from. In eukaryotes, that RNA-DNA duplex, the RNA is erased by RNase H. And then the DNA polymerase for repair sees the gap and fills in the gap. So two players are involved in eukaryotes. Somebody to erase the RNA and the RNA-DNA duplex, and somebody else to fill in the gap with actual DNA monomers. In prokaryotes, DNA polymerase number 1 does both. At the front of the enzyme, it's throwing out the RNA. At the back of the enzyme, it's laying down the DNA. So it's doing both jobs. Like that truck on the highway in the middle of the night, tearing up the old asphalt, laying down the new asphalt. It's a wonderful process. We're still not done. Even though we've gotten rid of the RNA, we still have Okazaki fragments. These pieces are not covalently bonded together. That gets done by another enzyme called ligase. And ligase is found in both prokaryotes and eukaryotes. So the RNase H is the one difference between proks and eus. the very specific names of Pol 1 and Pol 3 is specific to Prokes, and that's the only replication distinction you need to keep track of. Ligase you need to know by name because it ligates these two distinct DNA molecules together. Ligase, when it finds a 5' and a 3' end in close proximity, will condense them together. Now that's a convenient thing to do if I'm in the laboratory and I've got two DNA molecules and I can make them sit next to each other. I can throw in ligase and I can heal them up. So I can take a strawberry gene and stick it into a fish. I can do that kind of stuff. So recombinant DNA is going to require a set of enzymes like the restriction in the nucleases, ligase. We're going to have RNase H in our toolbox, DNA polymerase 1. We're going to have all these enzymes in our toolbox, and there's different reasons why we would want to employ them. So finally, we have the fully replicated DNA that we wanted from the beginning. But it took a bunch of participants. Primase, a DNA polymerase for extension, a DNA polymerase for repair, maybe RNase H if we're talking about a eukaryote, and ligase to finish that job. Sometimes students are asked to tell that story. Sometimes students are asked, what if I had a defect in my DNA polymerase 1? What would you see inside of a cell? So you have to think about, well, I would have my primase, so I would prime. I would have my DNA polymerase 3, so I would extend. And if I didn't have Pol 1, I could never get rid of the RNA, and I would never get rid of my Okazaki fragments because ligase doesn't put RNA and DNA together, it only puts DNA and DNA together. Students are often asked this. Yeah, we taught you how things are supposed to work, and then we ask you, how would things go? Can you hypothesize how it would go if there was a problem, if there was a mutational defect? Geneticists like to mutate things, and they want you to imagine what the consequences of that might be. So, semi-discontinuous, and we just got to think about some of the enzymes that are involved in the process of replication. Here's a diagram from your book, I believe, where they're showing that stuff. They did it a little differently from me. They didn't show the whole replication bubble. They focused on just one fork. They also don't like this idea that DNA is single-stranded in a cell, so they have a single-stranded binding protein to hold it and pull it away from the other strand. They have an enzyme here called helicase, and that is helping the double helix to separate into single strands without becoming twisted and knotted. So helicase is important. I didn't mention it because it wasn't synthesizing any new nucleic acid chains, so I kind of left it out. I didn't mention the single-stranded binding proteins as well. Here they've got the DNA polymerase for extension. They've got it held to the template strand by what they're calling a sliding clamp. They are showing the primase kind of living right there at the fork, so every time the helicase opens up the DNA, it's ready to lay down a primer. So they're showing some details, some of the things that I said, but some of the things that are important to them as well. You can see the original primer must have been back here at the origin, and we're just going to keep going on the leading strand. This is a primer that was extended. Now we jump back here to this primer, and now that's been extended. Primase is about to lay down another primer. This is going to have to jump back and extend that. So this is clearly our discontinuous lagging strand synthesis. And that's the way it really looks. This is just a cartoon, but it's an awfully effective cartoon, where if you know the names of all the players, the spinning blue thing, that's helicase. Well, it just flew in and then flew out again, that yellowish colored thing. Let's see, here it comes. That's the primase, and then it leaves. Notice how it left behind, it laid a little gold egg there. That's the primer. So there's the primase comes in, it lays down the golden primer. Boop. The purple things are the DNA polymerase for extension. The continuous strand, it's just sitting there doing its thing. It keeps getting fed more and more template, and it just keeps going. But look what's happening on the lagging strand. There's the polymerase. It's all done when it gets to the part that was finished. It gets handed to the primer by this swivel arm thing.
So it didn't have to drift around and find where it was going. It got stuck to the primer, and then it does its thing again. And it gets handed to the primer. And the green thing is the sliding clamp. They are hypothesizing that it takes a third sliding clamp to grab the strand, grab the primer, and then grab the polymerase. I think what's inaccurate about this diagram is they have things flying in like there's a pilot that knows where they're going. And I don't think that the primase flies in. I think the primase is sitting there attached to the helicase. They just want it out of the way so you can see what's happening. But it's kind of a fascinating diagram. The guys who drew this say that it's at the correct speed. They even have a little soundtrack. You can hear it, which I think is a big fat lie. But things seem to go at about this rate. And I think that's fascinating. I certainly can't draw it this way. When they tell me that leading strand and lagging strand synthesis are equal in speed, I couldn't quite imagine how that could possibly be. And this certainly says they are exactly the same rate because of this magical swivel arm. So it's kind of a nifty sort of thing. I think that animation will play. I don't think you can print it, but I think it'll play on the posted slides for you as well. Before we move right on to transcription, again, we have to stop like we did last time and talk about technologies that depend upon just this much knowledge. And so we'll talk about the polymerase chain reaction. We'll do that in laboratory. We'll see how it kind of has replaced the southern blot. But again, quite a lot of material to think about. I think we were in chapter 10 today looking at this. I think we're back to chapter 6 for replication.